Okay. So exam 2 is next Friday, week from today. Um, and the topics are everything. So remember that it's cumulative, so you need to be ready for old stuff too. Um, up through um, the first law for control volumes. Anybody have any questions about the test? It'll be open answer or something. Oh yeah, it's all just going to be calculations. So the way to get ready for it is to go through daily problems. And weekly problems and in-class examples work too. Basically, all of those problems that I assign you are, I'm trying to get you ready for the kind of questions that I'm going to ask on the tests. Um, yeah. Any other questions? Okay, so now we're done talking about the first law. So the next topic is the second law of thermodynamics. I think this is the most interesting section of this class. Um, there's a lot to wrap your head around. It's tricky, but it's also interesting. Um, so most of today, I'm going to just kind of outline what we're going to be talking about, the meanings of the different things. I'll set you up to do a few problems. The first problems we'll do will be pretty simple, pretty straightforward. Um, the second law of thermodynamics gives us two abilities that the first law doesn't. So the second law gives two things the first law doesn't. Um, the first one is the ability to measure the efficiency of processes. You can imagine in industrial applications, this is a really useful thing to be able to do. And the second thing is kind of more leaning towards like the philosophical side of things. But the first law, if you think about conservation of mechanical energy from physics 1. There's no ability of the first law to tell you what happens first and what happens second. The second law gives us that ability. So we can calculate the direction of processes. So when I say think about conservation of mechanical energy, imagine a case where you have like a skier starting at the top of the hill and you want to calculate how fast the skier is going at the bottom of the hill. Okay, well, the wording might say that the top of the hill happens first and he goes down a hill that's 5 meters high, and at the bottom, you calculate a speed. But there's no reason that it has to go in that direction. All the same numbers would tell you if the skier is going at that speed at the bottom of the hill, how high does he get before he stops? Every first law of thermodynamics problem, every conservation of energy problem could work in the exact opposite direction. That's not true using the second law of thermodynamics. there are three equivalent statements of the second law, and I'm going to list them from the most kind of obvious to the least obvious, but the most useful in calculations. Um, the first one is called the Clausius statement. And you have to be careful with Clausius. There are actually two things named after Clausius that are going to be really important to us in this section of the class, and they mean totally different things. So I'm going to try to just keep emphasizing that. But the Clausius statement of the second law says, I mean, you knew this by the time you were 10 years old or whatever, you probably made this connection. But maybe that's not true. But anyways, it's very simple, very intuitive. Heat only moves spontaneously from high to low temperature. Okay. It's not really obvious how that would be useful for calculations in most cases. Um, Really, the usefulness of this is that you use it to derive the next one. So this is very intuitive. And based on this, you can derive the next one, which is the Kelvin-Planck statement. Um, the second one of these equivalent statements of the second law of thermodynamics is the Kelvin-Planck statement. And this one is a little more abstract. So I'm going to give you the kind of the mathematical definition, and then I'll talk about how to think about it. But for a system, that's in contact with just one thermal reservoir, um, the work done over a cycle, and you can think of this as like a power cycle, is less than or equal to zero. Okay, so let me kind of break this down. So for the reservoir, think of this as a heat source, or what we'll call a boiler in power cycles and power plants. Okay, so what this is saying is, so a power cycle, think of an old like fast motion black and white movie where somebody's shoveling coal into a train engine. So what this is saying is, if that train engine only has the fire, okay, that's a thermal reservoir, that's the heat source, but doesn't have anywhere for energy to be lost, which would be like the smokestack, you can't produce work. Okay, so you can't So let me say, in other words, i.e., you can't produce work from a power cycle that only has a heat source. Some energy needs to be lost um, to a second thermal reservoir as exhaust. Um, okay, so you have to have some kind of cool reservoir also for energy to be lost to. There's no way to take all of the energy you gain from shoveling coal into a fire and use all of it to create work. Some has to be lost. Um, okay. Uh, this one is going to be a little more useful to us for calculations, not as useful as the third statement. Um, so the usefulness of this is we're going to use this idea to talk about efficiency, to do calculations about efficiency. And we're also going to use this to derive. So remember that first one was called the Clausius statement of the second law of thermodynamics. We're going to use this to derive the Clausius inequality, which is a totally different thing, unrelated, except that they both relate to the second law of thermodynamics. And the entropy statement of the second law. Okay, so we got these two. I'm definitely going to, at some point, be asking questions about these on quizzes, So you want to go back and like remember these things, remember these relationships. And then third, most important to us, is the entropy statement of the second law. And it says for any process, the change in entropy of the system, that capital S is entropy, plus the change in entropy of the surroundings is greater than or equal to 0. Okay. So this capital S is entropy, which has a very dry mathematical definition. It's not something that that you can easily measure or feel or anything like that. We'll talk about how to define that when we get to this. But this is the one that says, and I'm sure you've heard this before, that total entropy always increases. There's no way to decrease total entropy. It's important to notice that when you say entropy uh, can only increase. You're talking about total entropy. You're not saying anything about entropy in a single part of the universe, you know? So, yes, entropy in, you can decrease entropy, like your refrigerator is constantly decreasing entropy inside the cold part of the refrigerator. You can decrease entropy in a certain location. But in order to decrease the entropy inside the cold part of the refrigerator, you're increasing entropy outside of the refrigerator. And those increases more than make up for the loss inside. So the total entropy of the system and the surroundings is going up. Okay. Um, and like, what is entropy? Maybe you've heard of entropy talked about as disorder in some ways. Um, you can think of it as like, I think you should think of it as specifically thermal disorder. Um, so there's kind of a fixed amount of energy that's available. And if that energy is separated very strictly a, into energy in a very hot region and energy in a very cold region, then that's very organized energy that's very easy to use for thermodynamic processes. Okay. Um, you can have the same amount of energy where everything's the same temperature. And then it's not that you've lost energy, but that energy can't be used to do useful work to, for thermodynamic processes. So that's kind of the idea of entropy. You want your energy separated into high energy, hot, and low energy, cold, rather than all just mixed together at a single temperature. So, like when people talk about entropy death of the universe, have you ever heard of that before? That phrase before? What they're talking about is little by little, as processes happen, um, all of that organized hot energy and low cold energy are steadily mixing until everything is the same temperature, and then no more thermodynamic processes happen. Um, and I mentioned this, but I want you to notice one thing, get it in your notes. Um, the Clausius statement of the second law and the Clausius inequality are totally different things. So that's just kind of our bad luck. Um, and you have to know about both of these two things. They're both going to be really important to us. Okay. Okay, I don't have much to say about this first statement. That's kind of a starting point where we derive the other stuff. I'm going to start by talking about the Kelvin-Planck statement of the second law. Um, and one way you can think of this is that you can't use all the heat um, from a hot reservoir to produce work in a power cycle. Some of that heat that you gain has to be wasted, and there's just no way around it. It's a thermodynamic law. Um, and we're going to use this. So we'll use this idea to talk about performance of power cycles refrigeration cycles, and heat pump cycles. And the first problems I'm going to have you do are going to be related to this stuff here. And as we go through, I'm going to keep bringing this up. We'll see this over and over again. But refrigeration cycles and heat pump cycles are really the same mechanism. They work the same. The only difference is what your goal is. If you stand behind a refrigerator, there's coils in the back that are hot. And so a heat pump is really just, so if you're trying to use a heat pump to heat up your kitchen, you would have the coils facing out of your kitchen. That's a heat pump. And if you want it as a refrigerator instead, what you care about is the inside. But like a refrigerator is both of those two things. Okay. And for all of these, we're going to define performance as the utility, the thing that we're trying to produce, divided by the cost. The thing that we'd rather not produce it, but it's required to get the thing accomplished that we want to accomplish. Okay, so the first thing we're going to talk about is the power cycle. Later on, we're going to go into more detail on power cycles and talk about entire power plants and things like that. And the way a power cycle works is, so we have a thermal reservoir here. This is where the guy with the mustache shovels coal into the fire. We have the system here. And then we have a second thermal reservoir here. This is the cold reservoir. And from the hot reservoir, QH, heat gets added to the system. The Kelvin-Planck statement says that, okay, before I do this one, actually, let's, so we're putting in heat. We're outputting power. This is what we want. That's our goal. But the Kelvin-Planck statement says you can't only do those two things. You also have to lose some heat here, QC. Okay, unfortunately, that's required. And conservation of energy says that all of the energy going into the system has to equal all of the energy leaving the system. So QH is equal to W plus QC. So let's think about the performance. For this one, we're going to call the performance efficiency. I'll tell you why that's different than the other ones. Um, and we'll give it the Greek letter eta, capital Eta. So, what is the thing that we're trying to get out of a power cycle? Out of these three things, QH, W, and QC, what's the one we're trying to, like, the more the better? Yep, W, right. So this is going to be W divided by, and now what's the one that we're spending money to create in order to get W? QH, yep. And now we can use this first law equation to represent W as QH minus QC. So this is QH minus QC over QH. And now you can simplify that as 1 minus QC over QH. And we're going to call this efficiency because this is efficiency because it ranges from 0 to 1. Well, one thing that you can see here is that in order to have perfect efficiency, you need to have either zero heat being transferred out in the exhaust, which we know is impossible, or you need to have infinite heat going from the high temperature reservoir, which we know is impossible. And so the kind of questions that you're going to get asked on the homework are, it's going to tell you some stuff about energy that's transferred, through work or QH or QC, and you're going to have to rearrange this efficiency equation and the first law of thermodynamics to get what you want out of what they're giving you. It's algebraically pretty simple, but it's just an exercise to kind of wrap your head around like what you know in these cases, how to use it, So second is the refrigeration cycle. And like I said, a heat pump cycle and a refrigeration cycle are the same thing. So the picture is going to look the same for both of these, but we're going to draw the same things. We have a hot reservoir. We have our system. And a cold reservoir. And what we're trying to do in a refrigeration cycle is we're trying to take heat from the cold reservoir and output it to the hot reservoir. So this is our QH. Well, we know that that can't happen spontaneously. That is the Clausius statement of the second law of thermodynamics. You can wait for 1 billion years and you're never going to get your heat to just on its own go from the cold reservoir to the hot. So what we have to do is input some work. Anyone remember or know from outside experience what the form of the work is that has to be done in order to make this happen? Yeah.
You usually squeeze the gas.
Yeah, that's right. So there's a compressor inside the refrigerator, and if you compress a gas, the temperature goes up. So um, as what our system is the refrigerant moving around the pipes, and so the let's start right before you get to the hot reservoir. And the hot reservoir, like in a refrigerator, um, the hot reservoir is the room, the surroundings. Okay, you're trying to output energy to the room, and so you compress this gas to get it to a high temperature. You let that high temperature refrigerant go into the coils and exchange energy with the room. It's a higher temperature than the room, so energy is lost. Okay. Then once you leave the coils, you allow that gas to expand and the temperature goes down. And then you move that refrigerant through the heat exchanger in, like, for the inside of the refrigerator. And because now that temperature is lower in the refrigerant than the inside of the refrigerator, than your carrots or whatever, um, heat goes from the cold refrigerator into this colder refrigerant. And then you keep going around: compress, output heat, expand, input heat, and it goes around. Okay. Um, so let's think about conservation of energy. It turns out it works the same way as before, just everything's in the reverse direction. Um, so the stuff entering the system has to equal all of the stuff leaving the system. So you have, again, QH is equal to W plus QC. The performance uh, so we're going to call this not the efficiency anymore. We're going to call this the coefficient of performance. And this is the Greek letter beta. And again, we're going to calculate this as the thing we're trying to produce divided by the thing that costs us money to make what we want. What's the thing we're trying to produce? If you have a really effective refrigerator, it's taking a lot of heat, a lot of energy out of the carrots. And so this is our QC. And what's the thing you have to spend money to do to get that heat output from the carrots? I don't know why I can't stop thinking about carrots. What?
You spend energy in making the work.
The work, exactly.
Yeah.
Yep, exactly. And and that energy comes from electricity. You know, you need electricity to run the compressor, or you could do it manually, and then it would be manual work to run the compressor. Um, and we can rewrite this as QC over, so work you can write as QH minus QC. The reason we don't call this one efficiency is because that fraction can be bigger than 1. So efficiency just goes from 0 to 1. This can be bigger than that. And then third is the heat pump cycle. And this one has the same figure and conservation of energy equation as the refrigeration cycle. The coefficient of performance stupid computer. Is that is the Greek letter gamma. Is that right? Gamma? Does that look like a gamma? Let me make sure.
I think so.
Okay, let me just make sure. I think it is too, but gamma, yes. That's the one that makes the Hulk turn green. Um, and so this time, you know, it works the same as a refrigeration cycle, but the part we care about is different. This time, what we're trying to produce is we're trying to pump heat into the high temperature reservoir. So we have QH. The cost is the work. And again, we can rewrite the work as QH minus QC. So we'll write this as QH over QH minus QC. And I don't have any example problems with me today. If you have any questions on Monday about this, I'd be happy to go over some of them. But basically, here are all the equations that you need. Conservation of energy. Efficiency is equal to, you can write it as work over QH, or you can write it as QH minus QC over QH, or 1 over QC over QH. And you're just going to have to use whatever forms of those fit the variables that you're given, to solve what you want. With the refrigeration cycle, you can use this conservation of energy equation. You can use that beta is QC over W if it gives you W. You can use QC over QH minus QC if you're only given the heat transfers, that kind of thing. Okay. Like as a math assignment, it's a very easy junior high type math assignment, Yep.
So I was thinking about the older versions of refrigerators, which just use ice cubes as the coolant.
Yeah.
And how is that still a refrigeration cycle as well?
No, that's not a refrigeration cycle. That's just allowing. You have a low temperature thing that's the ice and the air because of the ice, and you have a higher temperature thing that's your food, and it's just allowing heat to transfer spontaneously from your food to the colder
So is
air.
there work being done in to cause that transition from cold to hot?
There's no work done because that's what heat does spontaneously, is go from high temperature to low temperature. Okay, so it's only in the case that so in a refrigeration cycle, you're trying to pump energy as heat from a cold reservoir to a hot reservoir, and that's when you need work. So what are the benefits of these? These measures of performance um, allow us to put let's say, stricter limits um, on thermodynamic cycles. So it's not just a matter of trying um, to get to an efficiency of 1 or something. If you know uh, some values for your heat transfers, you can actually put limits on this stuff um, that are more meaningful than just like 0 to 1 or whatever. Um, okay, I need to say one thing.
Well, if you got a furnace and heat pump on your house, you can find the temperature at where the furnace is more efficient to run than using the heat pump.
Yeah, right, that kind of thing, exactly. Um, okay, there's 2 facts that you need to. This is the last thing I'm going to say about this. So this is 2 facts you'll just have to trust me on. I'm not going to go through a derivation or anything, although the derivations of this stuff are pretty accessible. Like if you wanted to spend a ton of time working through it, you'd be capable of doing it. But um, I think for all practical purposes, let's just go with my word on this. Um, so the first one is um, all power, refrigeration, and heat pump cycles with perfect efficiency, let's say, oh boy. So how about all power, refrigeration, and heat pump cycles that waste no energy, um, and those are called reversible cycles, and I'll define reversible next time. Have the same performance, same coefficient of performance. Okay, that's getting kind of back into like philosophical stuff. It does, if you have no wasted energy, it doesn't matter how you define these things, the performance is always the same. I think the best analogy to that is like if you think about mechanical energy, conservation of mechanical energy from physics 1, think about the skier going down the hill. Okay, if you waste no energy at all, remember that a skier who goes down a normal shaped hill has a speed at the bottom if the hill has a height of 5 meters, right? Well, if there's no wasted energy, it's also true that a skier who goes down a hill that's 50,000 miles long and just at the tiniest little grade, if that skier still drops 5 meters over 50,000 miles, at the end of that, the speed is the same. That doesn't make any sense in our everyday experience because we're not used to things that waste zero energy. There's always energy being wasted. But if you have no energy being wasted, then it doesn't matter how you design these things, they perform the same. Okay. In practice, there's obviously good designs for a refrigeration cycle and bad designs.
Professor,
Yeah.
but isn't power the like one where the performance is locked from 0 to 1,
Yeah.
and the other ones can be more efficient than
Yeah.
one?
Well, it's not more efficient. It's just the way we're measuring it. Yeah. It doesn't mean that it's more efficient, but the numbers can the performance values can go over 1.
Okay.
Um, so That means if we analyze one reversible cycle, we understand the performance of all reversible cycles. Okay, so that's a nice result because you can imagine that we could design a theoretical, say, power cycle where it's easy to do the math, and then we could, whatever results we get, we can apply to any other cycle where the math would be harder to do. And then the second one here is you can use this fact to discover that for a reversible power cycle, the ratio of the heat lost in the exhaust, QC, over the heat gained at the boiler is equal to the ratio of the temperature of the cold reservoir divided by the temperature of the hot reservoir. Okay, so like if I redraw this picture, this hot reservoir has a temperature TC. Here's our system. This has a temperature. Nope, I did this wrong. This is TH. This is TC. This is our QC. This is our, God dang it, I did it again. This is our QH. This is our QC. And then we have our work. And so this is another thing that you're going to have to factor in, think about as you do the few problems I'm going to give you for Monday. We can establish ideal performance just from the temperatures at the reservoirs. So when I say ideal performance, what I mean is the performance that you would get in a reversible, a perfectly, a cycle that wastes no energy. You can figure out what that would be. So the fact that, so here's the coefficient, the efficiency of a power cycle. Eta is equal to 1 minus QC over QH. Well, we can figure out that if you have a reversible power cycle, the efficiency is 1 minus TC over TH. Okay, so that puts a very clear limit once you know the temperatures of your two reservoirs on what the efficiency can be. You can't exceed that. This is like a perfect power cycle. It's still pretty strictly limited. And we'll do the same things with the other ones. The coefficient of performance for refrigeration cycle is QC over QH minus QC. And that tells us that the ideal coefficient of performance is TC over TH minus TC. And then for a heat pump, the coefficient of performance is defined as QH over QH minus QC. And so the ideal coefficient of performance for a heat pump is TH over TH minus TC. Okay, so if you're designing one of these cycles and you're limited by what the temperatures are at your, what your high temperature reservoir temperature is and your low temperature is, you can't exceed the performance of these values. These are things that waste no energy. Okay, so that's something very meaningful that you can compare your actual values to see how much energy is being wasted. Any questions? Okay, that's all.